Hey class, we're going to finish up with our notes for 3.1, and we left off on example 2, which is asking us to find a minimum slope. Alright, so since we're studying extrema, we're finding a minimum of something, right? Now, if the original function is given here as this cubic function, it says find the smallest possible slope of a tangent line drawn to this curve. Okay, so what we're finding is the minimum of a slope. Now, how do we find a function that gives us slope? We know that that's the derivative. So what we're dealing with then is the derivative of this function, and we want to find a minimum of that derivative function. Okay, so let's think about that. So a slope finder, right? A slope finder is a derivative function. So f prime is the derivative here, which is going to be 6x squared minus 6x plus 4. Okay, so this is our slope function, right? This is our slope, finder or slope function. Okay, that's what we've got here. All right, and what we want to do is we want to find a minimum of this, right? We're going to find a minimum. Okay, so now it's back to what we were doing before. It's like, okay, they're saying find the smallest possible slope. This being our original function, what's the smallest possible slope? Well, get your slope finder or your slope function finder, and then what we want to do now is go through our steps to find a minimum of this, right? Okay, so what we need to do then is find the derivative of this function, set it equal to 0 to find our critical numbers, and then go from there. Now, I think this one, I'm not going to graph all of these, but in this one, because it's the first one where they talk about this, find a minimum slope, I am going to pull up the graph of these on a calculator. So what I did in y equals, I graphed the original function here. This is our cubic function, and then this is the derivative that we just found there. Okay, so the original is going to be a blue cubic function, and the derivative is going to be that red parabola. So if we look at that a little bit, I want you to just think about this a bit. Okay, so here's our cubic function, this blue one, right? Now, this one itself really doesn't, the original function doesn't have a minimum value, right? I mean, because we're not really talking about a closed interval here, we just got this cubic which is actually increasing on its entire domain, everywhere, and so there's no minimum there. But think about this now. What we're saying is, where is the smallest slope occurring, right? So we've got some slopes that are pretty steep, and then it kind of flattens a little bit, and then it continues and gets steeper and steeper again. Now think about that as compared to what we have for this, this derivative graph right here. Remember, a derivative graph is a slope finder. So these y coordinates are all representing slopes of this graph right here. So like as I'm moving kind of this way, these slopes are getting larger again. But where do I hit a minimum for a slope? That would be right here at the vertex of this parabola, because that's my slope finder, right? And if you think about it, if you're visually looking at it, at a certain point right in here, it gets as flat as it's possibly going to be, which would be right at that minimum point right there. Okay? Now, the graph itself doesn't have any mins or maxes, because that would be where the derivative would be equal to 0. And as we can see, this derivative graph, the red one, never crosses the x-axis, and that makes sense because there are no there's no horizontal tangent lines of this curve. Okay, so we can see that we're probably going to get our minimum slope somewhere, it looks like it's between 0 and 1 somewhere. Okay, so something to think about as we continue and do this analytically. All right, so what we want to do now is we want to say, okay, well, what's the minimum of our slope finder now, right? So we're going to take derivative of this and set it equal to 0. So really that's a second derivative of f, and that's going to be 3x minus 6. Now we're going to set that, or sorry, not 3, 12. Getting ahead of myself. Okay, to 12x minus 6. Now I want to set that equal to 0. So 0 equals 12x minus 6, add the 6. And I think our results will verify what we saw on the graph. If I divide that out, I get an x value of 1/2. Now take a look again. So when we did the derivative of this derivative graph to find a minimum, we're seeing that that x coordinate is about where it looks like it should be, between 0 and 1, or 1/2 makes sense there. Okay, so that is where our minimum slope occurs. But what we want to do is actually find that minimum slope, because what we're doing, remember, is finding, this slope right here, that's where it's this, the flattest, I guess, is what we'd say there. And so we want to calculate what that is. We know it occurs at x equals half, but let's see what that slope is then. So to get that, we have to plug this back into our slope function, which is this one, so into f prime. So f prime, and we know it occurs at 1/2. Okay, so I'm plugging that back into this function right here. And if I put that 1/2 in there, so I'm going to go back to my calculator here. So I had that function is right here. It's in y2. So if I would go to, if I go to alpha f4 and go to y2, enter, and then I hit 1/2 for my input, I'll put 0.5 because that's where I want to check what the slope is when the x-coordinate is 0.5. I get 2.5 for that. Okay, so 2.5 is my minimum slope, or 5/2. Either one's fine. Okay, so that's how I'm going to calculate that one out. So my minimum slope, the flattest or the smallest slope that I get for that graph, is going to be found by finding a minimum of our slope function in this case, right? So our slope function being the first derivative. So we take the derivative of that again, which happens to be second derivative, set that equal to 0 and solve for x. Okay, and then to find that slope, we put that into our slope finder. We know it's going to occur when x is 1/2. Plug that in, and we can get our slope, which was 2.5. Okay. So these next couple questions are referring to an application of this same idea. Okay. So we've already studied some particle motion type problems, but now they're going to ask about some max and min questions involving particle motion. So we've started with a position function. It says find the minimum and maximum velocity of the particle on this closed interval. Okay, so because they didn't give us a closed interval for this problem, that's why I didn't really test endpoints. We looked at it on the graph and we knew that our derivative, our slope of our cubic was a parabola. So our derivative graph was a parabola, which clearly had a minimum value, and so we were able to determine that the smallest slope would be at that vertex of that parabola. Now here this is a closed interval, and it's a little higher order polynomial. It's a degree 4. So we'll definitely want to go through those steps, test our endpoints, test our critical numbers, and then we're going to look for our mins and maxes of the velocity. Okay, so velocity being the first derivative, right, of the position. So s prime, which is the same thing as v, so I'm going to connect those two because I know that those are the same thing. So if I take the derivative of this, I get 4t cubed minus 12t squared and plus 12t, and the constant disappears at the end. And so I want to set that equal to 0, right? So I'm going to set this equal to 0. And to solve that, I think I can factor out, let's see here. Oh, no, I haven't done this yet. I'm not setting that. Let me back this up. Just like before. Okay, so this is our velocity function right here, right? So this is kind of like what I did in this step up here. I found the slope finder, the slope function here, my velocity function. Now to get my mins and maxes, I have to take the derivative of that now. So I want to do v prime now and set that equal to 0 to get my critical numbers of the velocity function. So v prime of t is going to be 12 t squared minus 24t plus 12. And I'm going to set that now equal to 0. And I'm going to factor out this 12t squared minus 2t plus 1. And so that's going to factor into t minus 1 and t minus 1. So it looks like t equals 1 is where I have a critical number. Okay, so I get t equals 1 for a solution. That's my critical number. Okay, And then what I need to test then is I want to test the critical number of 1, and I also want to test the endpoints of my closed interval, which are 0 and 3. Okay, so critical number is going to be 1, so I'm going to, remember now you're testing this, we're looking for a max and minimum velocity, so put it into your velocity function, so v of 1, and we're going to get that value, and I plugged that into my calculator earlier, I got 4 for that, and then endpoints, right? So we need to test our endpoints, and we're going to do v of 0, and that's going to give us 0. That's pretty easy. If we plug that in here, or sorry, into this one right here, we have t's in all the terms, that's 0. And if we do v of 3 for our other one, and if I plug that one in, I checked that before, that's 36. Okay, so this is everything we need to test. We need to do our critical numbers. Now our critical numbers, again, are going to be zeros of the derivative of whatever we're trying to maximize or minimize. We're trying to max and min of velocity, so derivative of velocity, set that equal to 0. Get your critical numbers. There was only one because it was a double, same number, so I got t equals 1. Okay, so we're testing that, and then we're also testing endpoints. And now of these numbers, we want to state the minimum and the maximum values, right? And those were velocity numbers. Okay, so we can see that our minimum is 0 when t equals 0. Min is going to be 0 at t equals 0. And our max is 36 at t equals 3. So the max occurred at an endpoint, and well, they actually both occurred at endpoints. So as it turned out, our critical number, was a relative min or max, but it wasn't an absolute in this case. Okay, so both the min and the max occurred at the endpoints in this case. Okay, so that's how we would answer that. Minimum is 0, okay, and that occurred when time was 0, and our maximum was 36, which occurred at time 3 seconds. So both at endpoints. All right. Okay, now next question, our follow-up here is to find the minimum and maximum acceleration. Well, what we found here was an acceleration function, right? So our acceleration function, v prime, we already found that, which is the same as a, which was 12t squared minus 24t plus 12. So we're going to take this a step further now, right? So what we're going to do then is find that derivative of that to get our critical numbers of our acceleration function. Right, so continuing on there, if we do our derivative of this, we're going to get 24t minus 24. And we're going to set that equal to 0. And we're going to get 1 again for that, right? Okay, so again, we're going to test, we're going to do acceleration now. We want our minimum and maximum acceleration. So in our A, so this is, you want to make sure you write the correct notation, right? Here I knew I was testing for minimum maximum velocity, so I said v of these, critical number and endpoints. And so now we want to say A of our critical number, and we want to do A of our endpoints. So A of 0 and A of 3, and we're going to calculate those out. If I plugged in the A of 1, I'm going to get 0 for that. And you can check that out, but that gives you 0. A of 0 is going to give us a value of 12, because that's what we're left with there. And then A of 3, and I've calculated this, A of 3 gives us 48. Okay, so our minimum acceleration, minimum acceleration is going to be 0. It's 0 at time 1, it looks like. And so that one did occur. That one did occur at our critical number in this case. So our minimum acceleration did occur at our critical number of time 1, and our maximum acceleration, is 48, and that occurred at time 3 seconds. At t equals 3 seconds, okay? And so that one occurred at an endpoint. All right, so hopefully that's making sense. Test your critical numbers, test your endpoints, find the largest and smallest values of all of those. So you have to, on the AP exam, they call this the candidates test, and you have to make sure you've tested all the candidates being the endpoints and critical numbers. Okay. All right, last one. So here, they give us an equation that is a position equation, okay? So position, they used x. Sometimes they use s, sometimes they use x. Either way, it doesn't really matter. Usually they use an x if they're talking about moving to the left and right. They use an x for that. But what they've given us for a graph now is actually the velocity of this position equation. Okay, so it's the velocity associated with this position function. Okay, so what do we want to do? We want to find where is the particle when it reaches its rightmost position. Okay, so just to kind of discuss this graph a little bit and what's happening here. Remember now that since this is velocity, we should maybe think about this a little bit. All of these values as we're moving, from time 0 all the way through time 4, what's happening with our velocity here? Our velocity is negative for the first second, isn't it? So what does that mean? Negative velocity. And in this case, since we're talking left and right motion, this negative velocity means this particle is moving left for the first second, right? And then between seconds 1 and 2, we have positive velocity, so that means it's moving right in this part. And now between seconds 2 and 4, negative again, it's moving back to the left. Now it's going to ask us, where is the particle when it reaches its rightmost position? So what we're really trying to find then is, what we want to do is find a maximum of the position, okay? So rightmost meaning, it's maximized position, because that's going to be our rightmost position. So what we want to do is we want to set x prime derivative of the position function equal to 0 to find a maximum. We're looking for a maximum of that. Okay, and really x prime equal to 0 is going to be this velocity actually equal to 0. And as it turns out, by our graph, we should do this analytically too, but the graph actually kind of tells us this, because x prime is the same as v, right? Where is that equal to 0? And we basically can see it. Now what we probably should do is say, well, x prime is equal to, and then we take the derivative and see that it's 12t cubed minus 3 times 28 is 84 t squared, and 2 times 84 is 168 t minus 96. Okay, so what we'd want to do is set this equal to 0 and solve it, and we'd probably have to graph that on a calculator to come up with those solutions. But if we do that, what we're going to find is that the zeros of this, when we set our x prime or velocity function equal to 0, we would see this exact graph, and then we could calculate for sure. We could calculate zeros on our calculator. We'd say that 1, 2, and 4 are the zeros. Okay, so those are our critical numbers. Okay, so what we'd have here then for critical numbers of x of t would be, when we set x prime of t equal to 0, we would get those t values of 1, 2, and 4. Okay, so to find when is the particle at its rightmost position, we want to find the maximum value of this position function. So what we're going to do is we're going to do x of 1. We're going to do x of 2, we're going to do x of 4, and then we also want to test the endpoints, which, as it turned out, one of our endpoints was one of our critical numbers as well, and so then we just have to test 0 as well, x of 0. And so for all of those, we want to see, what's the largest value. So if I plug these in, and again, I would use a calculator, because you're going to be plugging them into this 4th degree polynomial, which is a little bit of a hassle. So x of 1, when I plug that one in, I got negative 36. X of 2, when I plug that in, I got negative 31. X of 4, when I plug that one in, I got negative 63. And then x of 0, when I plug that one in, I actually got a positive 1. Now, if you think about that, it kind of makes sense, because it's been moving, when it started, it hadn't been, moving anywhere yet, and then it's moving to the left because it has negative velocity until it gets to, the first second. And when we tested it, its position there was at negative 36. Well, then it moved right for a little while, right, until we got to the second. It makes sense, it's a little further right, it's at negative 31, But then it starts moving left again, right, between seconds 2 and 4. And so that makes sense that at second 4, it's way further to the left. So actually it's, you know, its rightmost position is actually at time 0, right at the beginning. Okay, so maximum position, max position, meaning its rightmost position. I'll put that in parentheses, rightmost. Rightmost, that's kind of a weird word. Rightmost position is 1. And that occurs at time 0, at t equals 0. And we did all of our candidates here. We did all of our critical numbers, which are, you know, the zeros of the derivative, and then we tested the endpoints. One of our endpoints was a critical number, you know, 4 and 0, and of those the largest number is 1. Okay, so that's its rightmost position. All right, and that is it. That's everything for these notes.